Okay, today I welcome everyone once again to our platform, Mineral Mining. Mineral Mining is a platform that we've actually developed to disseminate information pertaining to mineral and mining in the country. Anything that has to do with mineral and mining, this is the best platform to learn, see it practical, the way it is done in the field, and also get to know the processes. My name is NC Gideon. Today, we will be looking at structures. How can we detect geological structures? How can we detect geological structures and actually use these structures in our reconnaissance stage, especially possibly at regional to local level? You don't just move into the field and start exploring. There are certain things you need to do in terms of modeling for prospectivity. If you are looking for a new field, a brand new field, a green field, it is very important that you understand the structural pattern of where you are going to. In short, it is the first recognized tool, the process in mineral exploration. Now, when we're talking about structures, what do we actually mean? Structures are actually resulting from tectonic forces that occur within the earth. When these forces occur in different magnitude, in different dimension, it brings different, it gives the rock different kind of pattern. It makes the rock to break, it makes some to compress, it makes some to stretch and all that. So you see different forces actually come into play and makes this rock to give different to behave differently. And when this rock behave differently, they give rise to different kind of structures. They can give rise to faults. What is actually fault? When we're talking about fault, we're talking about, we're talking about a very relatively, we're saying it is in fault. We are looking at movement to be actually noticed, just unlike fractures. So in fault, we can look at the fault plane. We try to study the fault plane, look at the fault tracks, the hanging. This is just a normal fault. There are different kind of faults, which we don't want to go into today. These structures can also be folds. You can see fold, it can become as a result of compression. It can give different patterns of fold. The fold can result giving rise to syncline, the anticline, and axial planes of the fold. Structural geologists try to look at different kind of attitude that actually result when fold occur: symmetrical, anticline, asymmetrical, overturned, and all different kind of folds. Another one that the geological structures we are looking at is fracture. Fracture, whenever these forces occur, there tends to be a kind of separation in geologic formation, such as joints and fold that divide the rock into two or more pieces. A fracture will sometimes form a deep features or crevasse in the rock. So as you can see, the fracture can be shear, it can be extension fracture. So you see, fracture differs. There are some fractures that could be fruitful, some might not actually be fruitful. Another one is shear zone. Shear zone. Shear zone is very, very important discontinuity. It's a very, very important structural discontinuity in the surface of the earth crust. It forms as a result, as a response to a homogeneous deformation, partitioning strain into planar or curvy planar high kind of strains. If you look at this, you can see this is not at 90, this is at 90 degrees. So when we have a shear zone, just like what happened in the gold field, most of the gold that we have in the anchor schist belt in Nigeria are formed within the shear zones. So it is very, very important we understand our structures very well, analyze them very well, and impute them in our prospectivity modeling before going to the field. Another one that could result as a result of tectonic forces acting on rock is cleavages. Cleavages can also form. When cleavages form, it makes the raw the it makes it just the tendency of the some of these minerals to align parallel to zones of weak bonding. As a result of forces, you see the minerals tend to break along curved surfaces without a definite shape. But fracture is a tendency of minerals. It's just like opposite of it. The fracture can just occur without any particular preference. So these are some of the major faults that give rise to mineralization. Now, what is the essence of these faults? Faults, the fractures, the shear zone, the cleavages, and all that. They are very important especially in the mineral exploration. Minerals do not form in vacuum. We understand that minerals form where there is a trap. Minerals look for a place that is conducive to form. So structures it forms act as a trap for some of the minerals we are looking for. Almost every mineral forms are actually controlled indirectly or directly by structures. So it is very, very important we understand what it means. So for you to be a writer, for you to have a very interesting way of interpreting your work in the field, you must have some attributes as a structural geologist. I think have to think widely, go beyond the 2D we normally see with our eyes. Those days in school, we always try to see fault, want to see fault, go to the field, want to see it locally where they actually want to say, sir, where is this fault? Where is this? Most of the times, if you've not done that, the essence of geophysics these days, through area photography, through some magnetics, through gravity and remote sensing, we'll be able to interpret and look at so many things, on a regional scale. Because going to the field directly as a person trying to define them, most of these things are subsurface. And mineral we are looking for are not on the surface, they are subsurface. So we need to understand that. Second one is the ability we need to think and interact largely with the other geoscientists to have a wide view range of geological and environmental problems. We also need to understand that we have to be able to link whatever we are seeing in the field and bring them into a kind of a shape, a kind of a computational modeling for us to appreciate them in 3D. What is the essence of the structure we are looking at? As I've just said, we just run through them. Definitely, they are very important in hydrocarbon and mineral exploration. Without structures, you can't talk about hydrocarbon, you can't talk about minerals. They form the major traps we have in industry today. Then second one is in the mining process. This is very, very important. This actually help you to understand how to put your addicts, how to put your tunneling and all that. So you need to understand the structures of the mineralization you are mining. If you don't understand that, it will be very important in planning your pits and your way down. Again, in terms of regional geophysical and chemical surveys for new provinces of mineral, it is very, very important. Then again, we'll talk about, it's a core when we are trying to interpret some geophysical, some geochemical, and geochronological data in geology. It is very, very important. Now, most of the structures we build, bridges, the dams, the tunnels, you don't build it on where there is weakly formed. You need to look at the formation structure. You need to understand whether there are underlying fractures, underlying faults, and all that before you put some structures on the surface. So it is very, very important in geotechnical studies. Also, in terms of earthquake prevention, This is very, very important. If we understand that there's a big relationship between the earthquake zones, prone zones, to that of structure. So we use this in earthquake seismology study. Now, there are mainly two ways we can acquire some structural data. We can acquire them from geophysics. As we just said, if you look at this, use a Google image area around Pakistan. You can see the coordinates here. You can check it yourself. This, you can see physically, you can actually, these are, you can actually observe the structures on the surface, you know. So you can look at it. Secondly, the gravity anomaly maps can also give us this. Then we can use radiometric. We can use radiometric. We can also use aeromagnetic. So also in remote sensing, we can also use remote sensing. When you talk about remote sensing, talk about the multispectral images like the Alstar and also the hyperspectral imaging. We can also use that in data acquisition. Then second way of acquiring data is of field. By going to the field, we can, looking at this image, you can see by PF ray, we can acquire some structural data from the field. We can measure the strike, the dip of planar features. We can also measure the plunge directions. We can also gather some information about the orientation of structures. So the magnitude and the strain sometimes can also be gotten where possible in the field. So the relative sense of displacement across the brittle, fault, and ductile shear zone can also be acquired. Cutting across, some relationship you can also get from measuring some structures, the joint, the fractures in the field. Also, the characteristics of the strain, the increment and the final strain analysis, when it's done, can actually also be gotten. The models we are trying to do, we've done, now this is, first of all, let's look at our regional area. This is our study area. Now, this is brand new field. You don't know anything on this area. You've not gone there before. And, starting an exploration, you need to increase your exploration from one confidence level to another. You don't just go in and tell your client to bring all the monies for you to fly a plane that you don't actually know and all that. So with this, you need to start with some data, possibly that are not, try to look for free data, try to look for some data from the government, try to look at some journals, some things that are actually done in such areas, some satellites, remote imagery, and all that. Now we want to show you, look at how water bodies or stream channel network can be of great excellence in structure. If you understand your network, your stream network, it would tell you so much about the structural pattern in terms of regionally in the area you are trying to work for. So, and this could go a long way in terms of reducing your cost ab initio. So, you see, let's look at this. Let's assume that, for example, you have your dam. Say you have your dam image of the area. What do? You can use your dam first of all, even if you don't have access to the topographical map. And sometimes the topographical map could be in hard copy. It might be difficult for you. You're referencing and extracting the contours and all that. So you might not be able to have some of the shape files that you require to do your modeling, but you can start from a very low key. This is the dam of the area we actually want to study. Looking at this dam also, we can see that already we are seeing a pattern. This is this area is a very high, followed by this area, and you can see an expression here. You can also see an expression from this dam. Now from this dam, we'll be able to work or can extract our our drainage network, look at it, where are the depressions and all that. What do? We can actually fill this dam. When we fill the dam, we'll have something like this. And after filling our dam, we can obtain our flow directions. You see, this is the flow directions we've obtained here. You can see the maximum flow directions. It's like a basin. Most of the basins will fall within these regions. You can see them. You can see them. You can see them. And areas of blue are areas of least depression. So this forms your accumulation. Your flow direction. Sorry. Then from this, we can look at our flow accumulation. You see our flow accumulation from what we've done so far. These are, you see, this forms your accumulation. This forms your accumulation. Then what do you do with your accumulation? From your accumulation, you can extract your possible water network. If you look at this, we need to also understand that the streams have order. Therefore, as the case may be in your project location. So the next one is we try to look at our stream order. You see, from the accumulation, we're able to get our stream order. This is the stream order. It means that this particular area is maximum accumulation. So we can see the dendritic pattern, and all these are the branches we can actually get from this. That means that the major orders will be this because this is the longest stream. So wherever other waters are coming from, they're going to join this one, the primary one. So this will serve as the first order kind of stream, and this sign, you can see this side towards the eastern part of it, you can see kind of first order stream. You can see this. So we've done order of this stream with different kind of colors. If you look at here, you can see this is blue, this is black, this is green. So these are different orders. Now, what are these going to help us in doing in terms of our structure? Then we'll look at the end of the day, we'll be able to get the stream within this location. Now, that is our stream. That is our stream. You can see our stream. Now, looking at this stream now, without any other data, we can actually start inferring some structures. Now, this stream, naturally, you ask yourself, why is this stream bending? Well, you can see, you look at angles. Look at angle, this is almost at 90. Look at this angle also at 90. Now, you look at the displacement here. This stream naturally is supposed to have been like this. You ask, what is actually happening here? Why was there a kind of bend here? You see? And if you look at this displacement here, there's also a displacement here. So if you look at this, you can infer that something is happening here. There's a structure here. So you can find out that you can actually infer that these water bodies are actually controlled by a fault. So you can mark this area as a place you can look at with other data. You can also look at this location. So, and you can also see that there is a parallel. This one is also running in parallel with this. This is also running in parallel with this. This is also running in parallel with this. So, where is the maximum fault within this location? So these are the things you actually start asking yourself. You see, everything depends on actually what you are looking for. If, for example, I started with a geological map most of the time, yeah, you might know the geology maybe in terms of broad sense. Is a metamorphic terrain, is an igneous terrain, or is a sedimentary terrain. But at this stage, you might not actually be able to determine what kind of rock is here. For example, you see, this is just, this is just a geologic map. The geologic map is so broad that you can see nothing is actually showing. On a regional scale, nothing is actually showing. It's just showing that this is a granite necks kind of zone. This is boundary. Also, you see, it just too bad at this stage, at this region, at this scale with what I'm working, it might not really be a good one to actually bring in to actually see the real geology of this location at the scale I'm working. So that's why it's very, very important that you understand and explain your structures very, very well. So now you've done this, you've actually inferred some faults, inferred some structures here. This is running, and you must also understand that most of the primary faults give rise to some conjugate faults and some auxiliary faults where the minerals are actually formed, or where the fruitful minerals we are looking for accumulates. So the next thing you might try to look at is, okay, you've inferred digs from the water networks. You look at, okay, let's just bring in our ground magnetic data we've done over the location. If you look at this, as this data, you can see what we are saying. This is one VD data, magnetics. You see, you can see that this is this location. You can see a boundary running here. You can see a boundary also running here. You can also see a clear boundary running at this location. So you can see that this place looks shared. Look at the expression here. It is not fine at all. It is, when I mean that it is not smooth, as in terms of, so clearly this will tell you that you are dealing with a metamorphic terrain. You can look at a lot of expressions that are distorted. Now look at where we've inferred the fault before. You can see break. You can see a break here. You can also look at here. You can see a break here. So you can look further in different directions. You might try to look at your X directions. You can see in X direction, you can see also the same break is still shown up here along this axis. You can see this location. We can see this. We can also see this. We can also see along these locations. So you can actually understand that this area is highly faulted. So we can group this area as a shared location. And you ask yourself, you want to go deeper into geology, what actually gave rise to this kind of thing. Now, it's clear that we are dealing with a metamorphic terrain. Then let's look at this. So let's look at this further. We can look at another. This is a 2YD. It's a 2YD. This is 2YD. That is in Y direction. We're trying to look at, we're trying to bring more of the expressions that are in this Y direction. You can see, so look at the first area. You can see the first area that the stream showed us. There's also a break there. You can see also, you can see here. Then you see, without any magnetic data, we've been able to look at what the stream's expressions are in this location. Now, if we do that of 1VD, you can see that most of the streams there actually follows boundaries and fracture zones. Okay, you can go further to look down to some of the data we've actually processed. You see, if you look at this rudimentary data is expressing a very clear boundaries in terms of lithology around here and also around this location. But our interest is actually in the faults and fractures we can pick from this zone. Now, having done this, we try to pick some of these locations. Now let's look at some of the magnetic structures we picked on this location. You can see coincidences. You can see what we are saying here. So definitely there is a displacement along this line. There is a displacement along this line. And you can see this also coincides with this. And along this line also there, you can see a lineament along this line. Also, if we bring in other structures, you can see that this water network also coincides with this as interpreted. Now, having looked at this, you will understand that these are the primary structures in this location. So the primary structures in this location can be named this, can be this and this. So if you are looking at prospectivity confidence level, we can look at this location in terms of structure, can look at this location. So this is actually what, when we put together, we'll be able to look for conjugate faults or look for some other secondary faults. Now, it is very, very important not to overlook some of these branches here, because actually if this is actually primaries, we are looking for an offset from the primaries. So this location is very, very important. Then apart from that, we'll now look at criss-cutting relationships. You can see some criss-cutting relationships at this location, where at the point of intersections are very, very important. You can look at this and this and this. So by looking at this, we can see some directions in the northeast, direction in the north-south actually, and in the northwest. Which one comes first and which one comes second? So these are the things we actually try to look at in this model. So with this, we'll be able to bring out a priority zone to focus in our local mapping. So, but at this reconnaissance survey stage, it is very important that all these things are actually understood. So with this, I think you've been able to at least have a first-hand information on how to interact with your limited data. So it's very important you know how to work at least remotely as much as possible, because of what we are into now. You need to actually understand that at least you have to do so much work, at least 60%, 50% of the work remotely, and try to go to the field and map out most of the areas you actually worked on in terms of when you are doing your truthing. So with this, I think you've gained some knowledge on interpretation of structures as a reconnaissance tool in your exploration processes.